Welcome everyone to this week's Autonomy Talks. This week is a great pleasure to have with us Professor Nadia Figueroa, who is the Shalini and Rajeev Mishra Presidential Assistant Professors in the Mechanical Engineering and Applied Mechanics Department at the University of Pennsylvania. And there she also has appointments in Computer and Information Science, Electrical and Systems Engineering, and also is member of the famous GRASP Lab. Something about Nadia, she received a Bachelor of Science degree in Mechatronics from the Monterrey Institute of Technology in Mexico. She then moved to Europe. She obtained a Master of Science in Automation and Robotics from the Technical University of Dortmund. And then she got her PhD in Robotics and Control from the Swiss Federal Institute of Technology in Lausanne, in Switzerland. So that's, we both got our PhD in Switzerland. That's nice. So before joining Penn, she was a postdoc in the Interactive Robotics Group at CSAIL here at MIT. And her research focuses on developing safety, control, estimation, and learning methods for collaborative human-aware robotic systems. In general, she focuses on robots that can safely and efficiently interact with humans and other robots. Today she will show some of this in her talk titled From Motion to Interaction, a Dynamical Systems Approach for Human-Centric Robot Learning and Control. As you have seen from her webpage, if you looked around a bit, she has a lot of cool videos and demos, and I'm very excited to see more of that. And also, I forgot to mention, she obviously has won a number of awards for this work, which is very impressive. So I'm personally very excited to hear more about it, and I give you the stage, Nadia. And in case you have questions, feel free to write them in the chat, and we will ask them along the way.
Well, thank you so much, Jolie, for that very nice introduction. So I'm going to just dive right in, right? So like what I'm interested in is in developing robots or deploying robots that can safely and efficiently interact with humans, right? Because any robot that anyone in any lab is developing is going to end up at some point interacting with a human or being deployed in a human-centric environment. So that's really what we focus on in my group, and what I'm really interested in solving all of those problems that entail having a robot like interacting with a human. In particular, in physical, very high-speed reactive interaction. So one of my dreams, or kind of like what I really want, is to have robots be able to interact in these type of scenarios, right? So like if you can see, this is a very busy kitchen of a Michelin star restaurant where they're moving around. They are sharing workspace. They're getting in the way of each other, and everything is still kind of like moves fluidly, right? So like there's a lot of interaction. Some people touch each other, some don't. Some kind of like try to avoid colliding. And all of these processing is done in real time, right? Like it has to be done really fast. So if we want robots to be able to, let's say, be deployed in these types of scenarios, then we need to think about how to make them safe, adaptive, and reactive, and having that kind of like real-time performance. The other kind of like task or application that I'm really interested in is in making robots that are actually useful for humans. So like physically useful. I'm pretty sure some of the millennials know about this this episode of Friends where they're trying to kind of like manipulate, co-manipulate this couch up a set of stairs. And oh, I didn't want to put the audio. But as you can see, like they fail, but they try, right? So like they're even with humans, this task is very difficult, right? Even with humans, this task is difficult. There has to be a lot of intention detection, figuring out what your partner wants when you're doing this collaborative task, when you have this limited like perception. So these are the problems that I'm thinking about all the time. Like, how can we make robots have these type of capabilities of being able to physically assist humans in useful tasks? But to our let's say what we really have right now in, like, let's say deployed is our robots injuring humans, right? Like if we see several articles online of like, oh, a robot broke the finger of a 7-year-old boy when it was, like playing a chess match, or robots severely injured or killed a human in a factory when it's supposed to be like in a very structured environment. And there's multiple of these, right? So like things like issues start coming up as time goes by, as people start deploying robots in human-centric environments, even in very structured ones, like a factory where there's supposed to be a lot of safety kind of like guarantees or let's say rules. So that's exactly what we focus in my lab. Like in my lab, we want to do human-centric robot learning and control. So like anything that the robot does in terms of the control, how it learns, it should always think about the human, that the human is going to be there. So how do we deal with that, right? Like how do we control and how do we learn for humans? So the three things that we're really interested in is fluid interaction, right? So developing controllers or learned policies for robots that will fluidly interact with humans, like in this video that I'm showing here, where we have like myself handing over a large heavy object to 2 arms, being able to physically assist humans in everyday tasks, basically figuring out what's the intent, the collaborative manipulation intention of the human, and being able to provide the necessary force, right? Like basically the assist that's needed, kind of like a paradigm of applying a force, being able to predict what the human wants, and then being able to do all of that in real time to actually perform the task with the human without making it more clunky or difficult for the human to perform. And then, of course, we want to allow robots to be able to swiftly adapt to changes in the environment, changes in the task, or even changes in the user preferences. So so we focus, like the main thrust in my lab are basically control for safe pHRI, right? So like being able to have real-time controllers that can ensure safety guarantees, right? Like the videos at the top where we can see like a very reactive collision avoidance on the left, where with in a workspace of a robot on the right with a navigation in a navigation setup. Here on the left as well, directly with avoiding colliding with a human, a very like a complex high-dimensional articulated obstacle, or even going more at the low level and ensuring that if the human physically perturbs a robot, how can we ensure that the robot doesn't go into self-collisions or go to joint limits while providing also like passive and compliant behavior? So those are some of the things that I will talk about more in depth later. I just wanted to give an overview of what we do. And then, of course, there's the efficient learning part, right? So from my point of view, what we want is really robots that can learn quickly, right? Like that can learn quickly or that can adapt quickly from a human preference or a human demonstration with as little amount of data that we need to query from the human. So my idea or my intuition is that we don't want humans to provide 100 demonstrations all the time for like different tasks, right? Like we would want them to provide the minimal number of demonstrations as possible, and then have the robots, let's say, squeeze or get as much information from that demonstration in order to perform the task in a stable manner, and while being able to allow perturbations as you see in these videos. So yeah, so all of these videos were trained with one or a couple of demonstrations. So this was kind of like the overview, and now I'm going to talk about how we do this, right? So before talking about how we do this, I want to give a little, like, kind of like get a little step back and really understand why our current robots, or the way that we control robots, from my point of view, is not thinking about the human at all. Like it's not human-centric robot control. And that's why we have all of these incidents all the time, simply because the way that we're controlling, or our control pipeline, is flawed or has basically the incorrect objectives and requirements for robots that are actually going to be deployed in the real world with humans around them. So I'm just going to lay out kind of like what I call the traditional robot control pipeline, which I've had some backlash for some people, but I'm fine. Like I think this is the traditional way of doing things, where you have some form of task specification, right? Whichever you favorite is the task specification you want at a high level. So you have some high level decision of what you want the robot to do. Then that high level planner gives, for example, a goal and maybe some constraints like X star and some constraints beta to a motion planner that then creates kind of like the trajectory that you want the robot to follow. And then subject to some optimal, some objective that you define. And then that is fed to a low-level controller that then tries to track that trajectory, right? And we normally we only have feedback at this lower level, right? At the low-level control, where we basically send directly the torque inputs or velocity or however that robot is controlled, and then we care about like the external perturbations or disturbance perturbations mostly at this level, at the physical like robot level. But all of these other layers are somewhat offline. So that's kind of like what like they say traditional robot control pipeline. So if we think about what are the objectives of this pipeline, they are generating an optimal trajectory, right? So for the robot, accurately tracking that trajectory as best as possible, and remaining stable or keeping stability of the robot at the low level control, at the low level, and obviously being able to reject perturbations. So if we think about these objectives, the assumptions of whatever system is going to be deployed with this type of pipeline is that if you deploy a robot with this type of control architecture, you're assuming that the humans will follow any safety rules that you tell them to follow. You're assuming that the human is not going to physically perturb the robot. And you're assuming somewhat that you have like a quasi-static or fixed environment that is basically that you use to generate those high-level decisions and motion planning layer here. Let me change to the laser pointer. Yeah. Okay. So what I want to argue is that these assumptions are not correct. Like these assumptions will not hold when you deploy robots in the real world. Why? Because humans will not follow safety rules. Like we don't even follow safety rules when driving our cars, which are more lethal machines than a manipulator on a tabletop. We will try to interact physically with the human, with the robot, because that's in our nature of physical interaction. And all of the tasks and the environments and even the preference definition will be dynamic. It'll always be changing. So if those are the correct assumptions, then my question is, do we really need an optimal trajectory? Do we really need to super accurately track that trajectory? And do we really need like that perturbation rejection layer only at this low level control? And that is what I question that, and I propose in my work, or this framework of saying we need to rethink a little bit how we control robots when they're deployed in the real world. And of course, I mean, you can any of these modules can be learning based, right? Like I'm not ignoring that part. But I'm going to the point where if all of this is an end-to-end system, then obviously it's not going to work either. If you don't have any feedback in between the loops. So that's exactly what I propose, right? So like what should change, right? Like what should we do in order to make the robots actually follow these assumptions of their during their deployments? And so what should our control objectives be for physical human robot interaction? That's the first question. And how do we achieve them? Right. So like those are the two things that I'm going to answer in the remaining time of this lecture. So first of all, assumptions, I said humans will not follow safety rules. So what are the objectives? Like even if the robot is tasked to just do like a pick and place task, it should still have a reactive low-level controller that avoids the human or any agent that's coming in its environment, right? We want robots to be able to handle human perturbations, because these perturbations can be either adversarial, like you see in the video here, where I'm just kind of like pushing the robot around to stop it from achieving its task, which is releasing the block in the target. But perturbations can also be intentional, right? It could be the case that the robot is performing a task and the human just wants to correct it quickly and say, no, don't grab this block, grab this other block, or don't polish this surface over here. And our robot should be able to allow the human to just come in, grab the robot and move it. And then the robot kind of like adapts or infers what the human actually is doing. Or wants or is saying like to change in the robot's task without having, you know, a very difficult or complex layered like architecture that deals with all of that. This should be kind of like natural in the way that we're controlling the robots. So for that, obviously, we need compliance. We need the robots to be compliant. And then the next one is kind of like dynamic tasks, right? Like if the tasks are going to be inherently dynamic, then we need our objectives is for adaptive planning, not optimal planning, but adaptive planning, right? So it could be both, but from my point of view, the objective is more on the adaptation part than on giving like an optimal a trajectory in terms of like time critical situations. Then obviously that's where you would need something like that. But in a lot of these adaptive tasks, what's more interesting is kind of like adaptation to the changes in the states of the world, of the human, and of the robot itself. So here I show some videos of what I mean by this type of adaptation. So basically my main thesis is that any skill that a robot learns should be safe and interactive and adaptive in real time. Should be without the volume. Okay. So how do we achieve that, right? So that's kind of like our the next step. So going back to this robot control pipeline, the only way that we can really achieve this is if we start adding feedback into the higher level layers that we have in our traditional control pipeline. For example, in the motion planning layer, as I said before, rather than generating this kind of like time indexed optimal trajectory, what we need is more of a reactive feedback controller, motion planner here that takes also the current state of the robot and is always adapting to whatever changes we have in the environment. And in order to achieve this, so this is kind of like the first chunk of theory or techniques that we use. What we do is basically we assume that the human and the robot motions are driven by a virtual autonomous dynamical system. So rather than representing the policy or like the motion generator, let's say a block of your robot controller as a function f of x that just gives you like the next desired state or a trajectory, we define the motion of the robot as a dynamical system like this. Where let's say like x is the position, x dot is the velocity, and f of x is this vector field or flow that's basically telling us from everywhere in the state space how the robot should move to achieve to follow that trajectory or to achieve or to reach that goal. And what's cool about this is if we formulate our motion policies in this way, then we can use control theory to ensure stability and convergence, right? We can apply Lyapunov theory and impose constraints on the parameters of this function f of x in order to have them have these vector fields have no local minima, no spurious attractors, and no divergences. So it'll always bring you back to the trajectory or to the distribution of your data that you use to learn these dynamical systems. You can also enforce safety, right? Like once you have a dynamical system, you can modulate it, you can reshape it. So you can enforce safety by this boundary-based kind of like invariance idea, similar to like control bearer functions. You can add a control bearer function on your state space, and then you start modulating the flow or encapsulating the flow of these dynamics to ensure safety or virtual boundaries in the state space. And of course, we can also apply even a more advanced nonlinear control technique like contraction theory, which is something that we're exploring currently in my lab to have even more expressive motion policies like limit cycles or motion policies that don't necessarily follow or are expressible with a typical quadratic Lyapunov function. So that's one cool thing, right? So like this, so if we formulate our motion policies as a dynamical system, we have all of these cool guarantees. So this already implicitly is kind of like showing or providing some form of safety to the robot, because we know that it's not going to do anything weird or erratic when it goes out of the distribution of the data, right? Which is kind of like a big deal in learning-based systems. But the other cool thing is that because it's just a very simple parametric function, we can do extremely fast adaptation with these type of motion policies, right? So in this case, this was a work from my PhD with my colleague and dear friend, Sina Mirasavi. And in this case, we can, as you can see, the video is slowed down 8 times because we can throw this like bar to the 2 arms, and what's driving the motion of the 2 arms is a dynamical system that we formulated to track the position and the velocity of the grasping points of these arms. So this is just to show you, like, if we can learn or parameterize these motion policies with these guarantees, then we can have really cool and reactive behavior at the level of a human or even superhuman level. So that's kind of like this part now, right? Like, so like the first idea is let's introduce feedback to this layer, right? Like, if we introduce feedback to this layer, then we can achieve these objectives of like adaptive planning and then being able to react at the low level and also at this more motion level. So this, I just wanted to mention, obviously, all of the videos that I showed before are on torque control robots that allow these perturbations, right? So like in this case, I just wanted to for completeness, I want to show kind of like how we control this robot with this very simple dynamical system impedance control law. So in this case, f of x is that dynamical system motion policy that comes from this block and provides the desired velocity of the robot at anywhere in the state space. And we simply use this this formulation to track. So it's kind of like a negative velocity feedback error. So this allows, depending on how we formulate this damping matrix, it'll allow the human to perturb the robot in different directions or orthogonal directions to the motion, or in any direction, depending on how we do it. But obviously, if we don't have a compliant robot, then this will be a bit more difficult to do. Not impossible, right? Like, we can have force torque sensors, tactile sensors to have put it on the robot so that we can detect when there's a touch or when there's contact, and then we can basically do this type of the same type of behavior, but now with a non-torque control robot. So then, okay, how do we get these? So I hope I convince you, like, okay, using dynamical systems is cool. Like, we can get all of these very nice properties, but how do we get them, right? Like, I mean, either we formulate them mathematically to figure out what we want the robot to do, but that's obviously very cumbersome. So how do we get these plans? And that's where we proposed from my PhD, and up until now, we've been proposing multiple techniques to learn these from demonstration, right? So the whole idea is that the human gives just a single or a couple of demonstrations of the task. We record the data, in this case of the end effector, so positions and velocities, and then we have multiple techniques now in my group to fit dynamical systems like these, like first order dynamical systems, to encapsulate and reshape a vector flow to follow that demonstrated trajectory, and with stability and convergence guarantees. So that's how those videos that I showed at the beginning actually worked. So we teach the robots with a couple of demonstrations. We learn the dynamical system motion policy, and then we just deploy it on the real robots with the compliant controller, and then we can get this compliance and robustness to perturbations and adaptation all inherently without having to do any like tricky decision making or anything like that. All because that's how we formulated the controller, and because we have feedback at these 2 new levels now. So I'm just going to go quickly on how to learn these, right? So this is very simple. This is a very simple machine learning problem. Actually, what we're doing here is simply it's a regression problem, right? So like what we're learning, if what we have is data of x and x dot, so like here we have these trajectories, right? So the red dots are the demonstrations. We have position and velocity data for each of the samples on our trajectories. So we can easily say, okay, let's just fit any type of standard ML technique to this trajectory, and we're done, right? So you could do that. But of course, there's no insurance, or there's that you will converge to the target, first of all, and that you will not have any erratic or divergent behaviors if you don't impose any constraints on these on this function of f of x that you're learning. For example, here I can show very, very quickly, like, okay, we learn this dynamical system with a Gaussian process. Of course, GP, like, it has very accurate reproduction, like when it's close to the trajectories here. But as you can see, we have all of these kind of like spurious attractors, and it doesn't even converge to the target, right? It kind of like just goes. So it can encapsulate and shapes the trajectory very nicely. But outside of the trajectory or the distribution of your data, you have no idea what's gonna happen, right? And actually, I mean, we do. Like, if it's very nonlinear, it's very likely that you're gonna have a spurious attractor there, and likely where you're outside of the distribution, it might even diverge. So of course, if we just use kind of like standard off-the-shelf methods, it's not gonna work, right? So like here, the idea is, if the robot is not perturbed and it's just following this trajectory, then it's fine. But what we're saying is, and we're assuming that the robot will be perturbed or is robust to any perturbation. So if you perturb the robot here, it'll end up kind of like converging to the spurious attractor, and then it will not achieve the task at all, which is what we don't want, right? Here's another example.
Nadia,
yeah.
There is a question in the chat from Maximilian asking, have you encountered any challenges when the demonstrated motions pass in close proximity to each other, for instance, on a figure 8 case?
Yes.
And how do you handle them?
Yes. Yeah. So figure 8 cases, right? Like, so that's here I'm showing. So the assumption for these first order dynamical system policies is that there are no self-intersections, because at least in this way that we're learning them, right? So because simply there's going to be a point where you have two potential velocities, right? So in those type of cases, what we do is then either learn it in second order, right? So like then we collect position, velocity, and acceleration, and then ideally we could learn the figure 8 or self-intersecting trajectories in that way. Another approach that we're also exploring, and that I like a lot, actually, is using kind of like some latent representation, where you project kind of like that your very complex dynamics into a latent space, where there you can essentially learn kind of like a very simple linear system akin to, like Koopman operator theory or manifold learning, and then bring it back to the state space, right? So for these for these right now, like the methods that we have that are very parametric, that I would say kind of like we're just learning the parameters, it's difficult, but we can do it in second order. We just need a little bit more data in that case, right? Because we need also the accelerations. Or we can use other more advanced methods to like shape these dynamics, which we are exploring. Yeah, and actually some people from Delft, I know of some methods that do that, and which is we were using this kind of like latent, like learning the metric and learning like that, kind of like how it looks in this high dimensional space. So yeah, so here is just introducing like the very simple, setup, but of course this can be scalable, and I will show later on that we can scale it to multiple more complex scenarios, limit cycles, and I don't have data yet about results for self-intersections, but I have a master's student working on that, actually, so soon we will have that too. All right, any other question? The other way of handling self-intersections also is then having like a higher level of segmenting your trajectories and saying, okay, like you have some goal-oriented first order system that is just switching, and then you can actually create that figure 8 as well. So that's something that we have actually done in practice. But then you need some segmentation layer that tells you like which trajectories are the ones that you want. Yeah. Okay. So yeah, so that's a neural network. Okay, so then, I mean, the main idea really is very simple, is using this theorem, right? Like using the theorem for global asymptotic stability for a dynamical system. In this case, the whole idea is that if we have a corresponding Lyapunov function, right, that represents your dynamics f of x, and you can satisfy this constraint, right? Obviously, like it has to be kind of like a with these conditions. So X star in this case is the attractor or the target of your dynamical system. So it should be 0 at your attractor. Should always be positive and monotonically increasing or rarely unbounded. And then this constraint is the one that if we enforce this constraint, which is kind of like the dot product of the gradients of your of a Lyapunov function and the dynamics is less than 0, then we know that your dynamical system is basically always dissipating energy and will always go to the lower level sets of your Lyapunov function. So then the whole idea is that if we have a dynamical system, if we learn a dynamical system subject to this constraint, then we can ensure at least stability and convergence to your target, right? So here I'm also just talking about single targets dynamical systems. We do have some ongoing work of like multi-targets dynamical system or multi-equilibria energy functions that are very useful for like joint space control or more high dimensional systems. Okay. Oops. All right. So I'm just going to go quickly through this. So this is just the one of the techniques that I proposed or that I worked a lot during my PhD in saying, okay, like if what we want is to impose this very hard constraint of from Lyapunov theory of global asymptotic stability, we know how to do that with a single linear system. Can we do it for how can we do that for a nonlinear system, right? So like instead of looking at f of x as a black box model, what we do is we create a more kind of like parametric model where what we do is basically say, okay, instead of having one linear system, we actually have k linear systems that represent our dynamics, and together with a mixing function that basically tells us when to activate one system and when to activate the other. And the key is that all of these linear systems should be stable with respect to the same Lyapunov function, so that when we mix them, then the resulting vector flow will end up being stable and converging to your targets. So of course, there's some constraint on the mixing function in order to achieve that, which is this mixing function should be between 0 and 1 and should sum up to 1, basically. So those are the constraints that we derived for this type of what we call linear parameter varying dynamical system. And one way to achieve this very easily is by using a Gaussian mixture model. So like in each of these ellipses that I show here, the whole idea is that for each ellipse, we have one Gaussian that is telling us you belong to this linear system, and then we learn a linear system that corresponds to each of these regions in the state space, right? So for example, for this region 5, we would have an A5 that is learned such that it just follows this flow, and then same thing for 4, 3, and 2, and 1. So when we mix them all together, then we end up with this very nice, smooth, and nonlinear vector field. So here we the whole idea is that once we learn that Gaussian mixture model, which I will give us a little details later of how we do this, because obviously one of the let's say caveats of this method is figuring out how many of these linear systems you need. So we do have an automatic way of doing this, actually almost in real time, to figure, like just analyzing the trajectory and just the position and the velocity data with a sampling method. But then once we have that, assuming that we have that mixing function, then the problem becomes very easy, and it's a semi-definite program. Basically, that we want to just minimize the reconstruction error of our trajectories with respect to those learned dynamics, the learned system matrices, and while imposing kind of like these constraints. So which is the one that ensures energy dissipation and convergence to the targets. So in this case, it's a convex semi-definite program if we already know beforehand what that P is. So we also have different methods to learn this actually in real time now, like given a trajectory, we can figure out like a good choice for the P matrix, which is basically shapes your Lyapunov functions to allow more nonlinear behavior. And then we run this semi-definite program in a very fast way. So just to show how easy it is to teach these systems and deployable, we actually have this method working in the MIT Museum in this setup. So here you saw how one of the the museum facilitators just showed a museum goer how to teach the robot how to do the task. And while she's explaining kind of like what's going on, then the motion is learned. In this case, it learns it in like 1 minute to learn the motion. So learn the motion, and you can see that the humans can interact very easily. So kind of like ensuring, safety and compliance to all of these to physical perturbations, and to also obviously the safety constraints. So here, one of the things that I glossed over a little bit in the previous slides is how to learn those mixture, how to figure out how many of these linear systems you need, right? So like, since we're using a Gaussian mixture model, obviously, like if there's no constraints on how the Gaussians are fit, then you would get some weird behavior, right? So for example, in this plot here, we use a typical Gaussian mixture model estimation technique just on the position data. And we get some Gaussians that from the machine learning perspective, it seems okay because you have kind of like nice data coverage with minimal number of Gaussians. But from our assumption that each Gaussian should represent a linear system, then it doesn't work, right? Because you end up kind of like combining these trajectories, which are actually moving in opposite directions. And then you end up kind of like having a dynamical system that doesn't really perform well. Like it will converge because it's learning your system matrices with these constraints, but it will just not it will not be able to reproduce very accurately your trajectory. So so multiple iterations. So this is just using position and velocity, as you can see, like on the trajectory data. It's a bit better, but it still does that mixing of like of clusters that shouldn't be together. So during my PhD, I proposed a Gibbs sampling based approach using a metric that uses kind of like cosine similarity on the velocity space, and it gives us this, but it gave us too many Gaussians, so it kind of like over segmented our trajectories. And it was quite cumbersome to learn, so it wasn't very efficient. And the more data that you gave it, the more time it took, because it ended up having to come up with a similarity matrix of all of the trajectories. So in a very recent work that we just presented at CASE, we presented what we call DAM, so directionality aware mixture model. In this case, we augment the trajectory data with like a projection of the velocity onto the manifold of the sphere, so that we can have like a nice metric of the directionality. And by doing that, and then combining it with parallel sampling, like Markov-Chain Monte Carlo, we can get super fast estimation of these Gaussians on our trajectory data. Very fast, that we can now do incremental learning, right? So like in this case, for example, my student Sunan, he showed one demonstration. We 3 demonstrations. We learned the dynamical system, and this is running in real time, actually, this video. And then you can see the dynamical system was learned, and now we have it here, the reproductions, and he will now show that reproduction. And because it's a parametric model, if you add more data or you add more batches, we also have a very simple way of adding those trajectories to our to the previously learned dynamical system, and figuring out how many more parameters we actually need to add. And all of this is learned in real time. So this video is just kind of like a screen recording of my students' desktop there. So as you can see, we do the reproduction and simulate the reproduction, and then now the robot is capable of performing that new task. All of this is within like a single motion policy, so we can incrementally build more complex trajectories and motion policies. Of course, one of the things, all of the variables that I have been using up until now is on X, right? Like, so you assuming Euclidean space. So we also have a new work that we extend now this idea of this linear parameter dynamical systems, but now at the quaternion space. And then we combine it to have an SE3, a full SE3 a linear parameter dynamical system with a Gaussian mixture model that is in the Riemannian space of the quaternion, combined with position space. And now we can also learn from a single demonstration, put it like the full pose, the dynamical system motion policies as you see in this video. Here we can see like a typical pouring task. See, oops. My computer's not moving. Okay, there we go. So on the left is just like without any perturbations. On the right, you can see that we can perturb, but because if it learned kind of like the flow in both position and orientation, so it's coupled. So if we perturb it, it'll also kind of like correct its orientation. And as you can see, that's a very useful task to have, and we even trust it so much that we're actually pouring real water on the cup. So of course, that's one way of learning these dynamical systems. We also exploring different techniques. So like using more kind of like virtual control approach, where in this case for cyclical tasks, we use a neural ODE with a couple of demonstrations of this kind of like a cyclical periodic task. We fit the neural ODE. One of the things of the neural ODE is that it encapsulates very nicely, very complex dynamics, but it still has that issue of spurious attractors and potential divergences. So what we did here was take a more of a virtual control approach and then say, okay, we stabilize our neural ODE, which is unstable. It's very accurate. It's very nicely representing very expressive trajectories, but it will go into some weird spurious attractors if it's perturbed. So then what we do is we add this virtual control, but which is very simple, this error, but it's on the but this virtual control is basically driven by a Lyapunov function that's on the tracking error of the trajectory, not with respect to a target or with respect to like a global attractor. It's actually with respect to your trajectory. So essentially, if you're perturbed, this virtual control will bring you back to that limit cycle or to that trajectory that was learned with the neural ODE. And of course, because it's a quadratic program, then we can add a collision avoidance with control barrier functions. So it's very easy to start adding constraints and make and ensure all of these different guarantees. We've also explored with a collaboration with some colleagues from Bosch and Denmark of using a contraction theory in the latent space, so neural contractive dynamical systems. These are also SE3 dynamical systems where we pass it through an encoder. And in that latent space, we then basically ensure that we have a contractive dynamical system with following this very simple contraction constraints, and then we deploy it. So we show kind of like even contraction in this latent space. In that paper, we also have some examples of how this works for learning motions of like a full human, more than 16 degrees of freedom human also. So all of this is cool, right? So like I showed you kind of like multiple ways how we go about learning these feedback motion policies in order to get like very efficiently, in order to get like that adaptivity that we want inherent in our motion policies. But then of course there's one other component of these policies are kind of like learn on static data, right? So you give a demonstration and it shapes your dynamical system following that demonstration, and it will only be able to perform that, right? Like if suddenly if your demonstration or if your task was all about going to a specific bio point or grabbing an object or avoiding some part of the workspace, and those geometric kind of like constraints start changing, then you will end up having to learn a new dynamical system, which is kind of like that whole idea of like multimodal learning trajectories from different viewpoints, so that they can be generalizable and transferable. So instead of doing that, instead of having to give another trajectory from a different perspective or from a different environment that represents the same task and trying to learn like this generalizable policy, we go about it a different way. So what we do is actually say, okay, we know we have some idea from the perception system of what are these task constraints. So they can be frames, for example, like frames that represent objects, SE3 frames that represent an object in the workspace, the target. the points of grasping an object, passing through a tunnel. All of these are objects that can be represented by frames. So it's geometric constraints, or even like in directions of approaching. So we said, okay, why, if this is all geometry, like if all these constraints can be expressed or represented by like geometric constraints, couldn't we add that into our motion policy so that when something changes in the environment, our policies or our dynamical systems morph with the change, with these geometric changes, instead of having to give another demonstration? And that's exactly what we did. So we presented this work last year at Coral. We call it now elastic dynamical systems. So the whole idea is very simple. So here I show you kind of like an original policy that was learned from a single demonstration, which is with the Gaussians and the vector flow. But now we add these like green blocks, which are our geometric task constraints, right? So like this is where you pick, this is where you place, and then maybe here it's like a tunnel or a biopoint. So if those change, so if those geometric constraints change, then what we said was, okay, in order to morph our dynamical system, all we need to do is morph those parameters to achieve or be close to those geometric constraints that we learned, that we know are inherent in the task. So what we do is basically manipulate that Gaussian mixture model. So we created an elastic GMM that now is basically the parameters of this Gaussian mixture model, which is a mixing function of our dynamical system policy, are the typical mean, prior mean and Gaussians, and also geometric constraints. So we added kind of like joints to connect all of these Gaussians. So now we have like a kinematic chain of Gaussians. So if any of the geometric constraints are moving, then what we're doing is basically kind of like solving an inverse kinematics problem, but at the Gaussian mixture model level. So this is exactly what we're doing here, right? So we adapt the GMM, and then we retrain the A's, which will change based on the new trajectory that we get with the adaptive Gaussian mixture model. And then that's exactly how we end up being able to have transfer. So task transfer and generalizability, simply by encoding like those geometric task parameters into our policy. So I can show you a video of how this works here. For example, here we give one demonstration. We show with that LPVDS framework, the original one, and then it deploys a task. And then now we change the orientation and position of the bookshelf in multiple ways, and you can see that what this method now adapts, right? Like what it's doing is reshaping or morphing your parameters of your dynamical system such that it now achieves the task constraints that you want. So the next step was, can we do this adaptation in real time for motion policies, for task constraints that are changing in real time? So that's the latest work that we have right now, which we call EMP, or elastic motion policies. So basically from a single demonstration or collection, here now we start introducing more perception, right? So we use, we track the Yumi gripper, we get the demonstrations directly from the human. We use also like a large vision-based model to tell us kind of like the segmentation points, and we track also the objects of interest. So, which is what initially we were doing everything with a motion capture system, and now we're using an actual perception system. So here, because of our advancements on computationally, that we can adapt these or morph these elastic dynamical systems in real time. So as you can see here, the EMP, of course, it can adapt to physical perturbations, as we've shown before. It performs the tasks nicely. So here we're perturbing it. We bring it back to another state, and then we change in real time. We're just changing the target, and it's immediately recomputes your motion policy without having to give any new data, right? So like here, the whole idea is that the robot kind of like the policy itself already has some notion of what is the task constraint, which in this case is the bookshelf pose that we're tracking using foundation pose. As you can see, the RGBD camera there, and the robot is capable to perform this, is capable to adapt them and perform this very nicely. So we have other things, of course, like the idea is all of these tasks are kind of like single tasks that I've showed you, kind of like which you can think of as action primitives or policies that are expressive enough but are not like multi-step long horizon tasks. And but because each of our dynamical systems have convergence and stability guarantees, then we can easily fit them into a high-level planner, for example, intertemporal logic, or this is a work that we just presented at IROS, or reactive temporal logic planning, where what we're doing is composing these dynamical systems, integrating with perception, and then being able to kind of like switch between systems depending on the states of the world or the state of the human, and the human kind of like comes in and starts changing things up, right? Start changing the task. So here in this case, we have that, and then we can also, here is another example of just having like a very nice composition of motion policies. Let me see. Nope. Okay, that didn't work. All right. So okay, so one thing that I haven't mentioned, so up until now it's all about learning, right? So how do we ensure then safety? So I've mentioned this before. So learning, and then we can also even feedback, right, at the high level decision, which is what this elastic framework is doing, is changing the target and changing the task constraints of our motion policy so that it's adaptive. So in this case, what we're doing is kind of like also feeding back some states, some information about the state to the high level decision maker. In this case, a very simple automata that we did for EMP, but then we're also exploring LTL in order to do that switching, to figure out what's the next dynamical system to use. But if we have these feedback at all these levels, then that's exactly how we can ensure like the reactivity at the task level, at the motion level, and even at the low level, right? So in terms of safety, I'm going to go super quickly over these. So I mentioned this before. When you have a dynamical system, it's very easy to modulate it, right? So if you already have learned a function f of x, and you have some representation of the obstacle, right? So in this case, you need kind of like some continuously differentiable function that represents your obstacle. You can essentially reshape your velocities, right? You can reshape your vector field. And this type of work is inspired by harmonic potential functions from artificial potential functions, but in this case with constraints, right? Like with guarantees of convergence, and at least not having the least number of local minima as possible, which is all of these reactive methods actually do. And one thing that's interesting is that this type of boundary modulation, of vector field modulation, is actually very similar to or equivalent to imposing a barrier function, which is something that we have shown in a recent work from one of my PhD students, was that if this modulation where we construct a matrix that locally reshapes your vector field such that it follows the border or like that boundary of your system, it's essentially performing the same thing that what a control barrier function performs. We have a paper under review where we compare them, and we actually have a new approach, which is a combination of modulation and control barrier functions to remove any local minima from any type of obstacles, because obviously one of the issues is like having very non-convex complex obstacles. This is showing just that idea with some recent work from that we published at TRO with Julie Shaw when I was there, with Chris Faria, who's the first author. He came up with this very beautiful on-manifold modulation, where if we have a single continuous representation of all of the obstacles in our in the environment, and it's twice differentiable, then we can see these isolines of our boundary of our obstacles as manifolds, and then what we do is we kind of like try to navigate around them. And this is what we are seeing here, right? So this shaded region, the red shaded region, is a single boundary function that represents the workspace limits and also the human constraints, the human in the task. So you can see we can do this modulation very quickly, right? So the whole idea is, if we have a good representation of our boundaries, then we can reshape our learned dynamical systems to be safe and also converge and achieve the task that we want. So this is what I'm going to go next of. this can be extended very easily to joint space as well, this idea, and we have done this, where we can easily sample from the joint space of a single robot, of a humanoid, or of multiple robots to learn a boundary function, right? So like we learn a self-collision boundary function from that offline data, and this is something that I did during my PhD as well. And then we can use that as a constraint, for example, in a quadratic program for IK. If you look at this constraint here, this is essentially control-bearer function. But then it can also be used in a dynamical system kind of like perspective. So here's just some videos showing a quadratic program, inverse kinematic solver with these learned self-collision constraints. Here it's kind of like we show for the humanoid robots. And then we went one step further and said, what if we learn the boundary function of the robot with respect to external collision, right? External obstacles. And that's exactly what we did in some recent work as well, where we sample kind of like the 3D space around the robots. And essentially what we're doing is we're learning this sign distance function. So this is a neural network where the input is the joints, the joint angles of the robot, the point of a 3D point in the space, and then what we get is this very beautiful, continuously differentiable boundary function that then we can plug into any of our reactive controllers, and which we did, which was this paper that we published in IGRR this year as well. It's a combination of MPC with modulation directly in the joint space. So one last thing that I wanted to note, or how are we on time? Because I have 15 minutes, but done. Let me see. Okay, I'll jump to this one quickly. Okay. So the last point that I want to talk about is a very recent work that we presented at RSS this year, in the sense that all of this pipeline, or like these objectives that we're achieving with this pipeline, or this way of learning, or this way of modulating and the insurance safety, they work if we know kind of like what is the task beforehand, right? Like if the robot was we already gave it like one training data at least, so we gave it a specification, like the LTL specification of the task of the multiple dynamical systems, and they were already learned. But what if the task is unknown or is undefined to the robot, right? So which comes to this type of task where, let's say we want the robot to actually physically help a human lift a heavy object or move it, like co-manipulate. In this case, the robot kind of like has an idea, like, okay, what I need to do is move, right? Like what I need to do is move this object probably to some position and orientation. But I don't know what that position or orientation is. And I also don't know how fast or how slow the human wants me to do this, or how much force I need to apply. So here, that's where the intention estimation problem comes into play, of like basically the robot in this case has some idea, has a structure of the task, but doesn't know exactly what the human wants. And this is what we did in this latest work. So the whole idea is that in this video that I'm showing you, the robot is computing or is estimating in real time the position and orientation of a very simple linear dynamical system that is just going to help you kind of like move objects around in 6 DOF, so in 3D position and orientation, so which is what we call here the task dynamics, right? So basically, based on if the human starts perturbing or pushing the robot is going to start estimating in real time a linear dynamical system, similar to what I showed before, like this A matrix, but now a single one for now, just because we wanted to see if this worked, for both the position and orientation, using a novel particle filter that we created, where the states of the particle filter are actually these parameters, are actually the targets of the dynamical systems and the linear system matrices. And then the particle filter, obviously, we can use some confidence about those estimates to then feed that into an impedance controller that starts modulating its force based on how confident it is about its estimate. So here you can see that working in real time in this case. These frames at the top are, so here we created like a game where we're telling the human move the pot to this position orientation, and the robot has no idea. The robot is just following kind of like the physical, the force, with its own proprioception, figuring out what is that desired position, orientation, and dynamics that you want, that it wants the human that the human wants it to perform. In this case, we're actually not using force torque sensors, because since it's a torque control robot, and we make it a little bit compliant, so like as soon as the human starts pushing, it uses its own proprioception to estimate this. So typically this is done with like admittance control, where you have the force torque sensor, and then you kind of like translate the those forces to some velocity. But that obviously is very impractical. We should have force torque sensors on any handle of any object. So we wanted to see, can we do this with like a dynamical system perspective, where the robot is basically estimating what the human wants, and that estimation is the parameters of a very simple linear system. So these are the new kind of like threads of work that we're working on in my lab of like intention estimation. Can we learn these more complex, let's say, dynamics or motion policies or intentions from humans in real time? And one thing that's interesting is that intention, when you're interacting with a human, there's two things that you should really, that the robot should know. What is the intention and what is the capability of the human? Like, can the human actually perform that task that it wants to do, like lift, so that the robot can then give you the proper force that you need. So in that case, we're looking into wearable sensors, so using EEG, EMG, and ultrasound sensors on the human to see if we can also detect kind of like the capability of a human. Because now we're thinking about, okay, what if we want the robots to help, people with muscular disabilities, elderly people to lift things and to do these physical tasks. In those cases, we need to also understand what are the capabilities of these humans. So that's just something I wanted to mention, things that we're exploring. And of course, we need to do all of this processing in real time. So this kind of like this muscle in the loop assistive robotics applications. This is what we're really interested in my lab currently. And yeah, so that's that was everything that I wanted to say. So basically, the two questions that I posed at the beginning of what should our control objectives be, my answer to this is reactivity at all levels, right? Like, you want to be reactive at the control, at the planning, even at the perception level, which is something that we're looking at. I didn't have time to present, of like what happens if your perception is faulty. You should be able to be robust and react to that as well, because these are very safety critical tasks when you're interacting with a human. And how to achieve this, obviously, with efficient models, with feedback and control theoretic guarantees. So I wrote a book about all of these ideas with my PhD advisor, Obillard, and Sina, my colleague. So it's online. For those of you that are MIT, it's there at the MIT library or the MIT Press. We're going to release it soon. We have a website for it as well. And yeah, that's about it. And I want to just mention all of my wonderful students and collaborators at Penn, and still some collaborators that I work with at EPFL and MIT.
Oh, thank you so much, Professor Figueroa, for your great talk. And Joel has to leave early for a faculty meeting, and he asked me to say sorry to you. And
Okay, no
there
problem.
are several questions in the chat, and I can ask them. So the first question is, well, in one of the latest work you used LLM, can you say again why? What are, in your opinion, the potentialities and limitations of LLMs in the control of robots?
Yes. I didn't put that one in here, but yeah, so that was like let me see. Oh, too many videos. Okay, but I can talk about it. Oh wait, I'm frozen. Can you hear me?
Oh yeah, I can hear you.
Okay, yeah. Oh, there we go. Yes, so actually, and so one of the latest works, which was this one where we do, okay, something's wrong with my slides, so I'm not even gonna try. So my thoughts on LLM is my students were very eager of trying to test like the limits, right? Of like, can we use them to sequence these like goal-oriented policies, or to at least tell us like what the human wants in a more long horizon task. It's promising, but my problem with it is that there's no way to kind of like control or let's say it's difficult to have any type of guarantees of what it's going to suggest, right? So you do need, like, if we're using LLMs, I feel like there should that we should use them not like in an open loop way, but also kind of like even in a feedback with the LLM of saying, no, this is not right, or this is violating some, you know, safety guarantee, and then have it, you know, have even a feedback there at the LLM level, so that you can kind of like guide it to give you like the correct answer or a better answer. What I've seen right now is that it works, and like you need to give it a lot of prompting, right? You need to describe it like the entire task perfectly, with all of the different variations of like, okay, there's a table, it's a kitchen, you have multiple objects. What you're gonna do is follow a recipe with a human, and then it starts. So that's what we did, was we say, okay, the LLM helping using the LLM to give us suggestions of like what the human wants to do next. I feel like it's promising, but there's still a lot of work to be done in if you want to have any type of guarantees about your entire control system, you know, your entire pipeline when you start plugging in the LLM. So there has to be some safeguards or some way of controlling it, or some way of figuring out like if it's correct or not, right? Like even using its confidence on what it suggested and taking that into consideration. Just using it as like, oh, in an open loop way, I don't think that's the way to go.
Okay, thank you so much. And another question is, the virtual control is similar to the shared control, right?
Virtual control. So in this case, it's it could be similar. Yes, yeah. I mean, in this case, what the virtual control, what we call it virtual control, it's more of like a, you know, controlled system where you have your function like x dot equals f of x plus g u, right? So like in the autonomous dynamical system, we didn't have the inputs, but now when we use in the virtual control part, now we have some inputs that is kind of like the stabilizer, right? So that's what we call we call it virtual control because it's a virtual system. Like it's not the actual dynamics of your robot. It's a virtual dynamical system that's telling you kind of like that's giving you the desired motion of the end effector. But when you do shared control, you're kind of like figuring out what to like which, you know, input to use, the human or the robot, and then kind of like mitigating that. So it could be a way of like mathematically it could look similar, but it's doing different things.
Okay, thank you. And another question is, when you say feedback at DS motion planner level, do you mean while executing the task or while learning?
Yeah, so that is while executing the task. But while learning is interesting. So it's while executing the task. So one of the current threads that we're looking at is, for example, if you saw in some of my videos where we can actually correct the robot in real time during execution. So then being able to learn from those corrections in real time, like the robot already pre-learned like a motion policy, and then the human just corrected it and said, okay, no, take this block instead of this one. Now we have the very efficient compute to be able to essentially update our policy in real time. So that's something that we're working on. But it's very interesting of like having some form of feedback during learning. Right. I think that could even make the learning. It might make the policy more robust as well.
Okay, thank you. And here's one question about the potential application in the field of surgical robotics. So yeah.
So in the field of surgical robotics, I feel like this type of framework could be very nice for like helper hands, right? Like let's say robots or mechanisms that a surgeon can just like grab, and then they detect the intention, and then, you know, like put the camera here, or put the you know, give me the tool or things like that. So like in a very interactive way. I do see that I do foresee that this can be deployed in those type of scenarios. In those cases, the safety has to be like even more, right? Like that we have to really try to ensure that whatever if the robots are going to end up performing something autonomously, then that's where the combination of perception and control has to be very tight, right? If it's kind of like in a semi-autonomous where maybe the surgeon is like semi-controlling it and the robot is inferring the task, I feel like in those type of scenarios or applications, that's where it could actually work. We do have the framework for this because we do have the real-time processing kind of like in at all the layers.
Okay, thank you. And here's one last question. And I was wondering whether incorporating RL here could help, and would it lead to learn considering safety as reward?
Yes. Yeah, yes, for sure. So a lot of the so basically, like, we can reshape these policies, right? If we have that boundary or like some reward or some function that is telling us like not go here, go here. This is safe region, unsafe region, or feasible region, unfeasible region, right? So definitely, I think this type of learning can be integrated into some RL framework. Like, I didn't talk about this, but we do have some work that also came from when I was at MIT, where we kind of like iteratively learn the boundaries of feasible motion from errors. So like from mistakes, like if the robot went into a region where it's like it was perturbed and it ended up not converging to the task, or it ended up like colliding with the environment, then we start adding kind of like hyperplanes to bound our vector flow. So yes, I think in this case, for that type of like bounding, right? Like, it could be for two things, for even to come up with your, let's say, Lyapunov function or energy function that represents the task, or as a way to bound your policy such that it's invariant and that it's feasible for the robot to perform, and it satisfies all of the safety constraints. For example, if you learn the boundary function with RL, then we can just plug that boundary function into this dynamical system framework, and it's going to work.
Okay, thank you again for your great talk today. Yeah, thank you so much. It's very insightful.
All right, thank you very much.
Thank
Thank you
you.
all for the questions.
Thank you. Bye.
Bye.